The operating system is a program that lets you interact with your computer. Together, the operating system and computer hardware form a complete system that determines what your computer can do. In other words, OS is the program that manages all of the hardware and software. It has control of all processes, files, parts of memory and devices. It works as a middleman, making sure both hardware and software interact correctly. Windows, Mac OS, Linux and Unix are big operating system contenders, and all have their own advantages and disadvantages, but they all are based on same concept. There are 4 essential managers of every operating system, and they all work together like a team to get jobs completed. The operating system works as their boss and makes sure they all work in harmony. Process can be defined as a program in execution. Every task we perform on a computer is made up of processes. Browsing, listening to music, printing a document, are all examples of process. The process manager decides how to allocate the brain of computer known as CPU. It is necessary that the process manager keeps track of the status of each process. It has to handle the jobs as they enter into the system, and manage each process that is associated with those jobs. Any process has 5 states in its lifetime: hold, ready, run, wait, finish. Think of a car race. You can't start the engine until the starting signal has been called. Now when your engine is on, you are in ready state. The ready state is a signal to continue with the process. When the car is ready to proceed, it is in running state. In our case, it is currently processing the job. Throughout this time of running, there may be a concern of performance. So a check with the team is made, to ensure it is okay to start running again. Returning to ready state, if it is okay to run again, it goes back into running state, but what if there is engine failure? In that case, an IO request page fault is presented, and the car is put in waiting state until it has found the correct resource, or a part, so that it can continue to run. This will loop constantly until the process has either completed or failed, where it is then put into finishing state. Based on the car race analogy, we can see that, when a process is created, it is in new state. Then, it is admitted into ready state, which signifies that it is ready to be assigned to the CPU. The scheduler dispatches the process into active state, if CPU is free. It means that the process is being executed. From the active state, the process can go to any one of 3 states, based on certain conditions. These states are ready, wait and finish. If an interrupt is received while the process is in active state, the information about the process is stored in process control block, and it is sent back to the ready state. If an IO or event is required for further processing, the process goes to wait state from the active state. After the completion of the IO operation, the process is sent back to ready state. If the execution of the process is complete, the process exits and goes to final or termination state. The process control block is used as an identifier, and contains basic information about the process. What is it doing? Where is it going? How much processing has it currently done? And most importantly, how much it has spent in using resources. Process scheduler is in charge of making efficient use of physical processor. There are 3 main types of process scheduler: long-term, short-term, and mid-term. The long-term process scheduler controls the degree of multi-programming. It executes much less frequently. It may need to be invoked only when a process leaves the system. Because of longer interval between executions, it can afford to take more time to decide which process should be selected for execution. The short-term scheduler, or CPU scheduler, selects from amongst the processes that are ready to be executed, and allocates the CPU to one of them. It must be fast due to frequency of execution. Medium-term process schedulers remove processes from memory, to reduce the degree of multi-programming. The process can be reintroduced in the memory later to continue execution. CPU scheduling algorithms are used to ensure efficient use of CPU by processes. These algorithms can be broadly classified in two classes. Preemptive scheduling. Process under execution can be interrupted, or preempted, and other process can be given the access to CPU in preemptive scheduling. If a CPU scheduling decision is made, when the process is either switching from active state to ready state, or from wait state to ready state, in such cases preemptive scheduling can be used. Non-preemptive scheduling. In this class of CPU scheduling algorithms, a process once given the access to the CPU, will leave it only after its execution is complete. If a CPU scheduling decision is made, when the process switches from active state to wait state, or when it terminates, there is no choice but to use non-preemptive scheduling. Some examples of non-preemptive CPU scheduling algorithm are first come first serve. In FCFS, the processes are provided access to the CPU, based on their arrival time in the ready queue. The process arriving first into the ready state, gets access to the CPU first. Shortest job first. In SJF, the process with the smallest burst time, or execution time, is selected from the ready queue, and is given access to the CPU. Priority. In priority scheduling algorithm, all processes in the ready queue are assigned a priority, based on some predefined criteria. The process with the highest priority, is the first one to get CPU. Some examples of preemptive scheduling algorithm are round robin. In round robin scheduling algorithm, a process in the ready queue, is executed for a fixed quantum of time, and preempted. This process goes to the ready queue again, and another process is executed, for the same amount of time. After one iteration through all the processes, the same steps take place, from the first process again. This loop continues until all processes have finished execution. Shortest remainder time. In SRT, a process in the execution is preempted, after a fixed time of execution, the process with the shortest remaining time of execution, is given access to the CPU.